Okay, so just remind you where we came from. So closing out this course with talking about dimensionality reduction and just a few methods. And we came from looking at linear spaces through principal component analysis to get lower dimensional data. We went from there to looking at possibly nonlinear structures by mapping those original dimensions up to a much higher dimensional system through nonlinear mappings, where if we have the inner products in that higher dimensional space, we can use that to do principal components up there. That was called kernel principal component analysis with a variety of choices of kernels available. And then we looked at beginning with distances and thinking about the distances between points, and rather than just use plain Euclidean distances for the distance between all pairs, to think about, can we just follow local distances around and hopefully follow around near a lower dimensional manifold that's possibly nonlinear. And with the distances following the manifold, we can then turn from distances to the Gram matrix, the matrix of inner products, and do the principal components again. Okay? So it's principal components and then two different reworkings of principal components, both the latter of which depend on knowing inner products. Okay? One inner products directly, the other inner products derived from the square distances along a local manifold, like the nearest neighbor network. So I just want to show you one more method that is much like the last one we talked about. Is trying to look at local behavior. And this is a simple method, simple-minded, and we can also follow the math, and that's what we'll do today, and then just see what it looks like. It has some shortcomings, which can also be turned into positive characteristics of the method as well. So the method's called local linear embedding, and as you might guess, we're going to use local information. We're going to somehow use a linear, local linear space to try and decide on what the structure looks like in the manifold. Then we're going to try to embed that in a lower dimensional space. So here's the algorithm. What we're trying to do is preserve the local distances. So I imagine any point x, the xith point in the space, and its neighbors. So I find the nearest neighbors by some definition. K nearest neighbors are all neighbors within a certain distance. Okay? And then I say, well, how could I use these neighbors to estimate that point value? So I want to think of that, of trying to estimate this guy from his neighbors. And I might do that by just taking a weighted average of the neighbors. Okay? So I take a weighted average of the neighbors. If I've got a weighted average of the neighbors, that's the best fit I can get to the actual value, right? Then I say, okay, I want to move this into a smaller dimensional space. That instead of the x's, I'm going to have some y's. And I'd like to be able to take any y and imagine estimating it from its same neighbors with the same weights that I had up here. Okay, so this algorithm says get the x's, get near neighbors, find a weighted average that estimates that x using only the neighbors, get those weights, take those weights, use the weights now, these are fixed here, and find the y values such that the prediction of the yi from its nearest neighbors, the same neighboring points, has the same weighted value, but it's in a dimension that I choose. Okay? So it's kind of weird, right? But you can see what we're trying to do is, can I fit this locally? Here's the structure of the fit. Can I use that local fit and make sure it works in the lower dimensional space? So the x's are fixed. I find the w's. W's are fixed, I find the Y's. And how do we do that? Well, that remains to be seen. Yep.
How many neighbors should I choose?
Good question. How many neighbors should you choose? Don't know. It's the same as we had with isomap, right? It's how many neighbors should you choose to get the local neighborhood graph. Should I use k nearest neighbors? Should I say everybody within an epsilon of the point? All good questions. Lots of choices. Okay. All right. So that's the logic. So everybody's got that logic because the rest of it's going to be detailed on how we actually accomplish this. Yes?
So just to understand this better, so you're converting, let's say that's particles in a 3D plot, then you just pick any one point and its neighbors.
Oh, I'm sorry. Okay, good point. So I'm picking one point and I'm looking at its neighbors. I'm trying to find the weights that will allow me to reconstruct that point so that it's a weighted sum of the neighbors are close to their, it's close to that weighted sum as I can get. Then I'm going to take the weights and find the y's. Now, what I'm going to do that, I have to do that for all of the x's at once. And you can see that these y's here correspond to some other, when I'm going to be looking at xk, right, at some point, sorry, xk and all of its nearest neighbors, it will have a whole bunch of weights as well. So those weights are going to get in the way of figuring out where the y will be here as well. It's got to be the same yk, so there's just all of these constraints on top of each other. Yeah, sorry if I glossed over that. It's all the points I'm going to do at once. For example, in 2 dimensions. So for example, this is 3 dimensions and I bring it down to 2 dimensions. Or this is 560 dimensional, I'll bring it down to 20. As essentially talking about the local fit and say, let's try and preserve that local fit in a lower dimensional Euclidean space. Okay? But it's a funny thing, but the idea is that you're, for any point, and we're going to do it for all points at once, for any point, I want to get a local fit that's not using very many points from very far away, but just its near neighbors. Take the characteristics of that fit and try to preserve those characteristics when I find new coordinates that are sort of flattened out into a smaller dimension. And a lot of methods are like that. They're effectively, can I get some local feature, hold on to it, preserve it, and make sure that the local feature is still there when I go down to lower dimensions. But I'm going to come at the cost of losing some global features. Okay, so it's kind of like isomap that way. Okay, are we ready for some math? So we're going to go through this slowly. They're online if you want to pull the slides up. So to be a little more precise, for every point x in our d-dimensional, high-dimensional space, we figure out which are the neighbors. So n sub I are going to be the neighbors of the point of the ith point. Okay, so it might be k nearest neighbors, for example. And then we want to find weighted values of everybody in that neighborhood such that we end up with something close to the guy that's the center of the neighborhood. And then we're going to do that squared length over all of the points. So I want to choose the w's to minimize that function. It's w's that give me the best estimate as a weighted sum of its neighbors, right, of that point. Okay? And to constrain it, I'm going to have all the weights of the points in that neighborhood summed to 1. Okay? So far, so good. So then I'm going to take these fixed weights, and now I've got a function of y. Y's got some target dimension which is much smaller than d. And I'm going to do the same kind of game here now. How well is the ith position being fitted by its neighbors? But now the weights are fixed, and this is a function of the y's. Okay? So that's the idea. Yep.
Well, why does the summation of the weights have to be equal to 1?
It's standardized. This thing is sort of ensures a bunch of invariance, but typically you're always going to have where the weights are going to be weighted some of the local guys, and they weight some. But all of these characteristics end up ensuring that we've got a lot of invariance going on here with common rescaling and rotation. And this is, if I translate the x's, which is that I relocate them, I'm not going to change things very much. So it's typically you've got a weighted average of the local points. And if it is kind of in the center, you're expecting that, that's the center of gravity kind of thing. Okay. So that's the algebraic expression of that picture. 2 steps, find weights, get the weights, find y's. So step 2, that's finding the weights. So I'm going to minimize this quantity, and that's peculiar to the ith point. So I'll give that a name, right? So that's a contribution to the ith point. All the weights in here are peculiar to the ith point, so I can call it wi, vector wi. Okay? So far, so good. So if I have these summed to 1, that just says that when I take 1 transpose times the wi vector, I get 1. Right? That's the sum of the weights. So now what do I want to do? I want to minimize this quantity subject to that constraint. We've seen things like that before. So I'm minimizing a function like this, a function of these Lagrange multipliers. And my function is that little piece plus a lambda times that difference. Right? So the thing is, the note is that, of course, what we're minimizing over is the weights and the lambda, and those are both peculiar to the ith point. So I can just look at this one piece by itself. Everybody with me? Yep.
So that, you said it was lambda, I'm reading that as 1 transpose, or what?
So this constraint, 1 transpose wi equals 1. That's an equality constraint, so I turn that into a Lagrange multiplier, make that lambda times 1 minus 1 transpose w, or 1 transpose w minus 1. Okay? So that's the Lagrange multiplier coming in there. It's lambda I because I've got one of those for every one of those vectors wi. Make sense? We saw that before, right? When we did when we discovered the principal components. It's just a Lagrange multiplier there that's ensuring a particular thing. In principal components, we're ensuring that the length is 1. Here we're ensuring that the sum of the weights is 1. So it's just another constraint. Okay, so everybody got that? All right. So this first bit. So we're looking at minimizing this function with respect to lambda I and wi, the vector wi. And I'm going to look just at this first bit here. That first bit is just this squared length. The point x that you're looking at minus the weighted sum of its neighbors. All right. So with sums are always easier if you can make them go away. You can often make sums go away with just re-expressing things in terms of matrices. So all I want to do is re-express this sum as this product. So I'm summing over Wi has elements, Wi1, Wi2 down to Wid, right? So I've got if xi is the d by however big the neighborhood is, number of points in the neighborhood, such that the columns of xi transpose are the vectors xj for every j in the neighborhood, then this guy, when you do the matrix multiplication, will just give us this. Okay? Because you're basically taking Wi times the ith column, sorry, Wij times the jth column of this matrix xi, and the jth column is xj for j in that neighborhood. Okay? So if I can replace that, I've got the squared length. The squared length is just this inner product of the vector with itself. And now I'm just doing expanding that, so you can go to good old FOIL, right? So it's just going to be xi, first, outside, inside, last, xi transpose xi minus first, outside, so do this one, Wi transpose xi, xi transpose Wi, that's this piece. And then the cross products here, it's going to be Wi transpose xi, little xi, which is this one, and then that's the last one, okay? So we're just distributing those multiplications. Everybody got that? Can everybody get that step? Anybody? Is that okay up there? Yeah, okay, good. So now the next step is a bit funny. Remember, I want to minimize this with respect to Wi, so it'd be nice if it was a quadratic form. If I just had the Wi's on the outside, because I know how to do that sort of thing. And so what I want to do is take Wi's out. Okay, so how do I take Wi's out? Well, if there was a Wi transpose on both sides of every one of these things, it would be great, right? So this Wi on the outside here, this Wi transpose out here, and that guy's in the middle, so that's going to be this guy. That's great. Now the next one is to think about, let's see, this guy. Well, let's do the first one, because if you get this one, the other ones just are simple. No Wi's. What a nuisance. But I know that Wi transpose 1 is equal to 1. So the secrets in doing mathematics are only two tricks, right? I think I've mentioned this before. Two tricks are multiplying by 1, and the other is adding 0. This trick is, how do you do multiply by 1? So we're going to multiply that on the left by Wi transpose 1. That's just 1. We haven't changed anything. And we'll multiply it on the right by the same thing. So I'm going to multiply this by 1 2 times. So if I had this as Wi transpose 1, xi transpose xi, and then 1 transpose Wi, I haven't changed anything. Okay? Everybody with me? Make sense? So it's just using the fact that Wi transpose 1 is equal to 1. And if I could do that, then this thing here is what's going to be in the middle. Because when I take Wi transpose inside, I'm going to get Wi transpose 1. That'll turn into 1. Take the Wi in this side, I'm going to get 1 transpose Wi. That'll turn into 1. I'll be left with nothing but xi transpose xi. These pieces are the same thing. I'm missing a Wi on the left here, so I'm going to multiply this on the left by Wi transpose 1. And that'll give me a Wi transpose 1, xi transpose Wi. Same thing here. I'm missing Wi on the right, so I'm going to multiply that thing by 1 transpose Wi. Okay? So there you have it. So now I've got this ugly matrix in the middle, but it's symmetric. And if you work that out, right, it's going to be the matrix of inner products. If I'm looking at I is what I'm interested in, right? So I'm going to look at xi minus xj transpose xi minus xk transpose. So the inner products of the difference between the guy you're interested in and two of the neighbors. We'll leave that as an exercise. Come back and we'll do it if we need to. So that's going to be some matrix. And now, in some sense, I don't care what that matrix is as long as I can calculate it. It's this mess, right? It is what it is. It's a bunch of numbers. It's symmetric. And so we're going to take, we've reduced this thing to the Wi transpose CW. And so what we need to minimize is that thing plus the part related to the constraint. So now we just need to minimize that. Okay? So you can differentiate that with respect to W. I. Yes?
How do you know C is symmetric?
How do I know that C is symmetric? Well, take this and take its transpose. Okay? So, so this thing is going to be itself again. This is going to turn into that. That's going to turn into that. And this will be itself. And now you can differentiate that. So that's just twice CWI minus lambda I times a 1 vector. Set it to 0. And that tells me that WI is proportional to C inverse times 1. Now I fix the constraint that 1 transpose times WI. So I know what WI is, at least what direction it is. I just don't know how long it is. Right? But I do know that it has to sum to 1. So I can get the proportionality constant just by saying, 1 transpose W, 1 transpose C inverse 1 equals 1, 1 transpose equals 1. 1 transpose C inverse 1 has to equal 1 for this to be the case, which means just divide by whatever that is. Whatever that turns out to be. Now we've got something that has the right weights. Okay? So that's W. So it turns out you can get W for every point. And if we can't get quite away with this, right, if that isn't quite there, it's nearly lower rank, the hack is to add a little constant to the diagonal. So a little ridge there to make it non-singular. Okay. Any questions so far? So you can do that. You could just differentiate that thing, solve, and enforce the constraint. So we got WIs, and now we've got little n of those. So we got W1 through Wn for all of the n points. Okay, now I need to find y's. And to find y's, I'm minimizing this function, but now the w's are fixed. Okay? So how am I going to do this? Well, I want to simplify this a little bit. And I'd like this to go away. And that could go away if I introduce, capital Y sub I, etc. But these things are going to share Y's across everything. So I want the same thing to appear, the same Y's to appear everywhere. I don't want just the Y's that are in that neighborhood, because I want to identify that these are going to be the same across different elements of this sum are going to have similar Y's. It's just which guy is here and what's the definition of that neighborhood. So I'm going to introduce a new vector. So I've just switched notation. It's a bit of a thing. I've expanded my W to be all the W's I had before, but I want to make them this vector, instead of just however many are in the neighborhood, I want the weights for all of the observations. So it's going to have n coordinates, not just however many are in ni. So if we're looking at k nearest neighbors, our old W would have had k coordinates, right? Because we're looking at k neighbors. And now I want to have n coordinates. But I know k of them are from our k neighbors, and the rest I'll just make them all 0. Okay? So that they're all disappearing. And it's just a way of simplifying it so I can write this sum as that, where I'm looking at all of the y's. So it's a funny definition. I've taken our original weights and just expanded it out, and wherever it's referring to a point that wasn't in the neighborhood, I get weight 0. So it doesn't give anything to the average. Okay? So you agree that I should be able to do this now, and I'm looking at with the rows of the y vector being of the y matrix being the y vectors, taking the transpose and taking this w, I'm going to get this sum. I'm going to get the wij for everybody that's in the neighborhood of the ith point, and then I'm going to get 0 times the y's that are not in that neighborhood. Okay? So that's what we want to minimize. Question?
So consider less neighbors step 3.
Nope. Same number of neighbors. So back here we have, it's just a notational change. So back here I have k neighbors, let's say we do k nearest neighbors, which means this w vector, since it's looking at the x's that are the k neighbors, it's going to have k coordinates, right? It's going to, according to which those neighbors are. Well, I could make that also, I could have made this a full-blown x here, and make that, have the w be a vector that is of length n, of n coordinates, and whenever, so the first point is in the first position, second point in the second position, etc. And wherever the points are in the neighborhood, I stick those weights in, and everywhere else I put zeros. So I haven't changed the neighborhood. I'm just pretending I'm taking the average of all of the points, except I get the weight for every point that isn't in the neighborhood is 0.
Okay. So you're making the length of the vector longer. You just insert
Yes.
zeros.
Yeah. So if I had, so let's say the k neighbors were, let's say I did 3 neighbors. So I'm looking at point I, and the 3 neighbors are 3, 17, and 27. Right? My first version of WI looks like this. It's got W, it's got a weight, it's got 3 elements. It's got 3 elements, right? And it corresponding to This is neighbor 3, this is neighbor 17, neighbor 27. Those are my 3 nearest neighbors. Now I'm going to say, I'm going to switch notation slightly, and I'm going to make this, say this was 1,000 points. I'm going to have 1, 2 through 1,000 here. 1 is not in the neighborhood, so it's going to weight 0. 2 is not in the neighborhood. Now this guy's going to appear here. 4 is not in there, etc. Down to at position 17. 0s down to position 27, and then 0s all the way. So I made that switch. Okay? It's just a notational trick so that I can multiply this vector by all of the y's.
So you could also do this in step 1.
Yeah, I could have done that in step 1. Okay? Or rather step 2. Step 2 and 3, not 1 and 2. So when I do that, it looks like that. That sum there. Okay? And the reason I didn't do that in step 1 is because it really, the weights only depended upon the neighbors here. The y's now depend upon lots of neighbors, right? So y17 may be the neighbor of 50 points, 50 different points. And it will also have its own nearest neighbors. Right? 3 and 27 may not be the nearest neighbors of 0.17, although these 3 are the nearest neighbors of another point. So I want to get all of the y's together because we have to do this minimization over all of the y's at once. Okay? The previous sum broke up. I could do these one at a time. So you could just minimize this entirely for each I. The w's are there. Now this minimization is going over all of the y's at once with different wi's appearing. Okay? But these are constant. That's the important thing. Those are constant. They're known. Are you okay? Does everybody get this? So I mean, you can just see this is what we're doing, but the reason for doing that is because these y's, the position of any particular y, depends not just on its neighborhood, but who is it also a neighbor of? Right? It's participating in determining the position of another point. Right? So there's all this interconnectedness. And that wasn't the case before when we were just looking at the x's. Yeah?
Sorry.
No problem.
Is it because you reduced dimensions, so it's possible that some guy wasn't
Nope.
neighbor before,
Nope.
now it's my neighbor?
Nope. Could be exactly the same sort of thing. I could say the same dimension, whatever. It's not because of that. It's because the way points are, right? I mean, this guy here could have these 3 points as its nearest neighbor, but now there are 3 more points closer to this guy, but farther away from that. So this location is going to be affecting these as well. Can you see that? Right, so I could have a point here where its 3 nearest neighbors are like this, but this guy's 3 nearest neighbors are here. So his location is going to be affecting this guy's location. His location is going to be, but it's also affecting this guy, who's maybe the nearest neighbor of that one. There's just more cross connection between the neighborhoods. So it all depends on how the data are configured. And so what I'd like, because the determination of this location is going to, it has to be the weighted average of these three, but this guy has to be the weighted average of these three, you know, and this one has to be the weighted average of maybe this, and the third point over here. There's just all this connection. So I want to get all the y's, recognizing that this y is going to be involved in the weights of this one. It's also going to be involved in the weights of some other ones. It's going to appear in lots of places. And so by making some of the weights 0 in that vector, I can just turn it into that and say, those are all the y's. For some I, the weights will be 0 for lots of them, for some other i's, etc. Okay? All right now? Okay. Oops.
So are there different weight vectors?
Yes. So different, yeah, so back here, that was the beauty of back here, is that this sum, we're minimizing the sum over all of the x's, but every point gets its own weight vector depending upon its neighborhood, right? So here. And because on its neighborhood, when we're thinking about minimizing this function, it's actually minimizing the sum of a bunch of functions that are disconnected because they all have their own weight function. So I can take them one at a time. Not so when I've got this thing. It doesn't break down. Those y's are all over the place. That is, even though I can't break this into a bunch of n different pieces, they're all mixing up across because we're looking at the y's now, not the w's. Okay? Alrighty. So same trick as before. Here's the sum. So so just quickly, we're looking at that squared length, right? So we just turn that in. So the length of x squared is just x transpose x, Euclidean length. So we're just doing that here. That's that sum. I'm doing that expansion just as I did before. Okay. And now I'm separating these pieces. So I've got the first piece, another piece, another piece, another piece. And every one of those pieces abstractly looks like that. For some m, some ai, some bi. It's some quadratic form, right? So for the first one, ai is yi, bi is yi, and m is the identity matrix. For the second one, ai is wi, bi is yi, and m is this matrix y. Okay? But the point is they all look like that because now I'm going to just show you a little trick. Okay? So they all look like that, and that allows us for some simplification. Here's a simplification. It's just how does matrix multiplication work? So imagine I've got a matrix A, right, whose rows are A1 transpose through AN transpose. Another matrix B whose rows are B1 through BN transpose. Right? The rows are AI transpose and BI transpose. If I were to take this matrix product of those matrices like that, I'm going to get a square n by n matrix, and its elements are, if I look at how that works, I got AM, there's the B transpose matrix, just taking that little transpose off. And to do that multiplication, I'm going to take first this matrix M times the first column, then in the second column I'm going to have matrix M times the second column, etc. Right? So that's the matrix multiplication result there of M times B. M times B has just got M times B1 in the first column, M times B2 in the second column, M times Bn in the last column. Okay? That's how matrix multiplication works. Now I've got this A matrix here, which has rows A1 transpose through AN transpose, and that product MB transpose. Well, how do I get the 1, 1 element? of that product. Well, I'm going to take the first row of this times the first column of that. That's the 1, 1 element. How am I going to get the 1, 2 element? First row of this times the second column. That's the 1, 2 element. Okay? So anyone here, it's going to be the ijth element is going to be the ith row here times the jth column there. That's how matrix multiplication works. So the whole thing looks like this. Right? Now what's cool about this is the sum that I want is actually that diagonal. So if I had this matrix, I took its trace, which is the sum of the diagonals, that's that sum AI transpose MBI. Okay? And that's what I want. Because any one of these guys looks like this form. Any one of these has got that kind of form. Just depends what the A's and B's are, and the M. So I want a sum like that for my choices of A's and B's and M. And the point is, if I form this matrix AMB transpose, all I'm interested in is the trace of AMB transpose. Okay? All right. So this sum, they just said this is this trace of AMB transpose. And now you know some cool things about traces. The matrix multiplication of traces, you can cyclically permute the matrices, and you haven't changed anything. So trace of AMB transpose is a trace of moving the B in front, and the AM, then moving the M in front of the B. So it's trace of MB transpose A. So one of these may be more convenient than the others to play with. Okay? So, crashing on. So if we take this W matrix, right, it's now going to be an n by n matrix. So we've got n vectors that are each n long, and the vectors, the weight vectors, are the rows of the W matrix. So this thing here, these sums, I'm just replacing this sum of yi transpose yi with the trace of the products of appropriate matrices. So y transpose, that's a trace of y transpose. This sum is the trace of that product. This sum is the trace of that product. This sum is the trace of that product. And the trace of a sum of matrices is, the sum of the trace of matrices is the trace of the sum. Okay? So this, you can actually factor, is that product. Everybody with me? The rest is just cycling stuff around, pulling out common terms. So pulling out the y here on the right, sticking in the middle, pulling out the y transpose on the left. So I get these guys in the middle. Identity minus W transpose. Cyclically permuting these things to end up with something which looks relatively nice. The trace of this matrix where I've got y's on the outside. Okay, so I guess maybe we can do this at the beginning of next day, but let me just try to get through this quickly. We'll pick it up again next day because there will probably be lots of questions here. So I need to find the matrix that minimizes this quantity. Okay? So this thing is going to be invariant under rotation and relocation of the vectors of y, since everything is distance spaced. And so the solution, and the solution must also be equivariant. It must change in the same way to common rescaling. Moreover, this thing equals 0. So if I project if I multiply these matrices together, I'm going to have 1 minus W1, and just the way that the W's work, they all had to have length 1. I'm going to end up with 1s again and have a 0. So that's going to be 0. So we can restrict the y's that they have to have average of 0. Okay? Now, so each column of y is going to be orthogonal to 1. And then the hack here is that the authors suggest also that since these are centered, this y transpose y is kind of the ellipsoid of where the points are, and they're trying to make them all the same, sort of a circular thing, and that's an identity matrix. Author hack, okay, that's not my job, but this is the procedure. And if I have that, we're not going to get through all of this, are we? Yeah, so this is the last slide. So we're looking at something that minimizes that, subject to this constraint. So adding an extra constraint, and that every column of y's are orthogonal to the 1 vector. I'll tell you what, we're not going to get through this. Any questions of this part? Well, just let's try to get this nailed. Does that make sense? Okay? That makes sense. This is just algebraic manipulation using that definition of that W and the matrix Y. And then characteristics of trace. And so now we're going to be back to this, and this is where we'll pick it up next day, I guess. So this shouldn't take too long, but I'm happy to spend, 10 minutes on it. Look at this. I'll tell you what, look at the slides, because they're online, before next day if you have a chance. And just go through this and make sure that you've got it. Because it's important that you get the ideas here. So yeah, I guess the thing is that you're using local stuff, local fit, trying to preserve that local fit. And these are just a couple of cute tricks that I thought you should see. Matrix tricks. That something that looks horrible, you can actually make kind of work for you. Okay? All right, till next day. The idea here is that we have all of our data in some large dimensional space. The data are marked as x's. And we look to use the local data near every point we're interested in to estimate that point. And might do that in a variety of ways. The simplest way is just as a weighted sum of the nearby neighbors. So you need to identify what is the neighborhood of that point and figure out what these weights should be for the weighted sum. Then once you have the weights, we think now about holding the weights fixed and generating positions y in a lower dimensional space such that when we estimate any particular y by its weighted sum of its neighbors using the same weighted sum, we get a close approximation to y, okay? So, on the math, it has the following pieces. So we begin with every point in the large dimensional space. We find its nearest neighbors defined in some way. For example, k nearest neighbors. That'll be a set of points that are peculiar to that particular index, the ith point in the data set. It's a set of neighbors. And then we look at finding weights, which minimize this sum of squares effectively. So we're looking at estimating any point xi by a weighted sum of the points in the neighborhood of that xi. And looking at that, the distance between the point xi and our estimated value of xi, and looking at the squared distance, and then summing those squared distances over all of the points. Okay? And I've added a little more here to the slides just to point out, I mean, this method is, doesn't depend upon the orientation of the points. That is, we could rotate the points any way we want, reflect them in fact. If you were to replace every xi and xj by a matrix O times xi xj, where O is an orthonormal matrix, or an orthogonal matrix, it's columns and have orthonormal vectors, then you will not change this function, the subjective function R of W. It'll be exactly the same. Similarly, if I rescaled everything here, if I multiplied every the xi's by xj, I still will not have changed the function in any important way, in the sense that it'll just be some scalar multiple of this function. So minimizing that, it's not going to have any, it'll have the same solution. Okay? So we've got some invariance here to common rescaling and to rotation. And then, as I said last day, we're going to assume that the weights sum to 1. And that's fairly standard to think about having an average of a weighted average of some number of vectors where the weights sum to 1. It has the additional advantage that if you choose that to be the case, then that we've got this also an invariance here to translation of the x's, which means if you were to take any one of these x's and add a vector a, add that same constant vector a to any of the x's, you'll have an xi plus a here minus the sum of wi times parentheses xj plus a. And you'll end up with an a minus the sum of wij's times a. And that will be a minus a times 1 minus the sum of the wij's. And so if that's the sum of the wij's is 1, that becomes 0, and there's no change just by having by moving the location of all the points. Okay, so it's invariant to location changes, to common rescaling, and to rotation or reflection. Okay, so that's that thing. And then once we have the weights, so we're going to find the weights by minimizing this function, and then we're going to find points in a much smaller dimensional space by minimizing this function over the y's. And last time we had a fair bit of discussion, but when we're looking at this function here with the minimizing over the w's, the wij, so they're peculiar to each j in any neighborhood ni, so that you can take the neighborhoods apart. You can separate this sum into the sum over the I and look at each piece individually. Whereas here, these wij's are going to be contaminated across because, oh sorry, not wij's are the same, but the yj's and the yi's are appearing in all sums. So we had some discussion last day about that. So quickly, we're just making this point again. If we've got this sum that we're going to try to find the w's, we can do that by minimizing each one of these pieces individually, right? Because the wi's all separate. It's just the sum of these different r's. Subject to this constraint, that suggests a Lagrange multiplier. So the function we're actually minimizing is this giwi lambda I that has the piece that we're interested in minimizing and the constraint. Okay? Any questions? Okay, let's get quickly through this. So we discovered last day that we can, with a little bit of work, we can express this quantity that we're trying to minimize as this nice quadratic form in the w's, which means you can differentiate it and solve. And when we differentiate and solve, the solution is going to be that wi is proportional to whatever that matrix C is, inverse times 1, and we just have to make sure that its inner product with 1 is 1. 1 transpose wi is 1, okay? And I mentioned again, aside, there's a hack here that if C is not really invertible, it's nearly singular or is singular, the authors add a little bit of a ridge there along the diagonal to make it non-singular. Okay, make it invertible. All right, now this step, we're looking at, we've got the W's are fixed, so we're looking at finding the Y's. And again, we're going to rewrite this function. Whenever you see the squared length, we're going to turn that into a quadratic version here. And then we notice that with a little bit of manipulation, this is just a sum of a bunch of forms that are very similar to one another. That is that they have a vector transpose on the left, some matrix in the middle, and a vector on the right. So a vector on the left here is yi transpose, matrix in the middle is the identity, the vector on the right is yi. Here it's wi transpose, the matrix in the middle is capital Y, the vector on the right is yj. Okay? They all look like this special form. And that, then we took a little aside. Just if I built up these matrices, right, the A matrix where every row of the A matrix is one of those vectors, A1 transpose through AN transpose, and similarly B has the rows B1 transpose through BN transpose. When I look at this matrix multiplication, I end up with an n by n matrix whose diagonal elements are the pieces that I want. And that means I can change, looking at the sum of these diagonal elements, and just call that the trace of that matrix. Okay? So this sum that we want is a trace. Trace has nice properties. We can cyclically permute the matrices. So trace of AMB transpose is trace of B transpose AM, trace of MB transpose AM back again, cyclically permuting. So that's a nice thing about traces. I can just move the stuff all around. So back to our problem. When we look at our problem, it was this mess. And introducing that Y matrix that we had before, this is just going to be trace of Y transpose, all of these pieces here. This is just the expansion of that product. Taking out the common factors of Y here on the right and Y transpose here on the left. I now have Y transpose in the middle. Using the properties of the trace, I can put those Y's on the outside. Okay? So now we want to find Y's to minimize that trace. Okay? So I think that's kind of where we were at the end of last lecture. In 10 minutes instead of 50. Any questions? So far we're just fooling around. It's not obvious that you go this way, but if you were doing this, trying to develop a method, you'd be fooling around seeing, can I simplify this in any way? And so the authors are going to be doing this sort of manipulation, see if it looks like I can get things on the outside in some sort of matrix form that I might recognize. So we need to find this matrix to minimize this quantity. And there are some funny things about this stuff here. So one is that we know by the definition of the W's, the W matrix, each row of W is going to be one of those W vectors. So we know that vector inner product with 1 is 1. Right? And I know when I take IN times 1, I get 1 back. So this thing is going to be 0. Okay? Everybody get this? This will be 0. So now look back up here at this piece here. And imagine any one of the columns of Y. Right? Those are the columns of Y are like one of the variates for all of the individuals, right? And so if I wanted to change the location of that one, I would just add a constant, say A, to every one of them. So I'm adding a constant to every value in that column is the same as taking that column and adding A times the 1 vector. If I do that, I haven't changed anything. So when I take that column, which is now the y column plus A times the 1 vector, and multiply it by the matrix I minus W, the 1 part's going to disappear. So I can make that A anything, and I haven't changed the problem. So there's no loss of generality here. I make all of those guys have mean 0. Okay? So the y's are going to have mean 0. So they're going to be centered around the origin. Okay? Everybody get that? Great exam question. Now, everybody get that? So it's not written here in the slides anywhere, but you have to imagine, what is this guy, I mean, it's just stated, what is this guy going to do to any one of these column vectors? And these column vectors, where did I define y? Maybe it's the next one I make it clearer. Yeah, here's where I make it clear. So we're looking at this quantity here that I need to minimize. And I'm going to think about every column vector of the y matrix, capital YJ now. So distinction between capital Y and little y being the rows, capital Y being the columns. These are the different variates. These are the dimensions. So again, I can center this without any loss of generality because I'd just be adding, I'd be subtracting off, minus y bar times the 1 vector, which doesn't change this thing I'm interested in. And if I work this out, we know that trace, so it's going to be trace times some horrible matrix in the middle, the horrible matrix in the middle being this guy, this product. That's M. We know that trace is just the sum. Every one of those yi vectors, those capital Y vectors, will be have mean 0. They'll be orthogonal to the 1 vector. And then I want to think about, well, how would I know that the 1 vector, for example, 1 times m, this m here, is 0. So the 1 vector is proportional to the eigenvector, an eigenvector that has eigenvalue 0. This is a real symmetric matrix in the middle, M. And so now you can begin to see where that hat came from. I said before that if we take this to be the case, and that says that all of those columns have to be orthogonal to one another. Those things are starting to look like basis vectors, right? We want all those guys to be orthonormal vectors. So it looks like an orthonormal set of basis. And I know that the 1 vector is proportional to the eigenvalue, proportional to the eigenvector that corresponds to the 0 eigenvalue. And all of these y's, every column, are also orthogonal to the 1 vector and orthogonal to each other. And I'd like to minimize these quadratic forms involving m for each one. These are going to correspond to eigenvectors of m, those that are orthogonal to the 1 vector. Okay? Everybody get that reasoning? Because we've done this before when we did principal components, right? If you're minimizing that, trying to find y1 that minimizes this, and we've constrained them to be all orthogonal to one another and orthogonal to the one vector, and the one vector is proportional to an eigenvector of this real symmetric matrix M, we're just off to the races to get these are eigenvectors. Eigenvectors correspond to the smallest eigenvalues, smallest p eigenvalues. Since we want to minimize this, smallest p eigenvalues of the matrix M once you get past the one that's associated with the one vector. Okay. Make sense? Not written out in detail, so this is your last go. Does this make sense? So you're going to have a think about this. Okay, so last time, that's some matrix, some real symmetric matrix in the middle. I'm trying to minimize the trace of this thing. The trace is going to amount to minimizing this sum, which is I can minimize these in turn. If I force these yi's, capital Yi's, to be orthogonal to one another and orthogonal to one of the eigenvectors, then I know they're going to be eigenvectors because I want these to be minimal. Okay? You've done that. That's principal components. So you know the answer. Okay? Let me do one last thing here. Y transpose Y. So any questions on that? Because I'm going to go back to a statistical thing now, away from this algebraic piece. Everybody got that algebra? Okay, so this Y transpose Y, if you think about that now, every column of that capital Y matrix, think of that as the Y on the, so think of the first column, that's the Y on the first variate, the first location, minus its average, minus the Y bar for that thing, right? That'll be also the first row of Y transpose. So when I take the inner product of those, I'm going to get the summation roughly of yi minus y bar squared. Okay? And all I'm talking about is what's happening in the 1, 1 location of that Y transpose Y. So I'm going to be looking at the summation of these guys minus the average, which we've made to be 0, but minus the average squared, okay? So that looks like that's proportional to the variance, right? The variance would be that divided by n minus 1 or something, right, as an estimate, or by n for a maximum likelihood estimate. Same thing for the next one when I do the second column with the second column. All the diagonal elements of this thing are going to look like proportional variances. The off diagonals are going to have, you think about the ith row of this Y transpose matrix, that's going to have all the Y's associated with the ith column, right, minus their average, times now the jth column, this way, ith row times the jth column, right? I'm going to have all of these guys associated with the ith variate subtracting off their average, all these guys associated with the jth variate subtracting off their average, their inner product, I'm going to have match the first ones and the second ones, etc. It's going to look like summation I equals 1 to n of like y1i minus its mean times y2j minus its mean. It's going to look like a covariance. Yes? Correct. Oh, no, they're not all equal to 0. That means that I've already subtracted off the averages. All the averages are subtracted off. so that they are orthogonal. I'm forcing that to be the case. I'm forcing that to be the case. Again, it's back up here that this doesn't change if I change that. So I may as well make them all equal to 0, average. So I subtract the average. But having subtracted the average, when I form this matrix is going to be the matrix of the sums of squares and cross products, right? If I just had 2, let me have an x and y because it makes the language easier. So it'd be like I have summation xi minus x bar squared in the 1, 1 position, summation yi minus y bar squared in the 2, 2 position, and off diagonal I've got summation xi minus x bar times yi minus y bar. So it's got the covariance. This thing here is proportional to the variance covariance matrix of the sample. And what we're saying is that that's actually proportional to the identity, which means when we get to the end of this, we're going to have y locations such that there are going to be no correlation between them, right? And they're all going to have the same spread, at least as measured by the standard deviation. So they're going to be roughly in the same box with no linear structure in any direction. And so again, this looks like an interesting hack to make it look like we can actually get somewhere immediately by picking off the eigenvectors, but it also doesn't look too badly thinking about it from a statistical point of view. We're going to map things in so they're roughly in this spherical cloud centered at the origin. Okay? With no correlation in any direction. No sample correlation in any direction. All right? Does that make sense? So there's a lot here. There's a lot to think about what's going on that this kind of makes sense. Any other questions? So you have a rule. You can now go and figure this out and get these values just by looking at eigen decomposition of getting the eigen values and vectors of this matrix and finding the p plus 1 smallest ones. You know one of them is going to be 0. It's going to correspond to the 1 vector, and you want the other ones. Okay? Right. So, just as we had with isomap in this dim reduction package, we could use LLE, define the neighborhood with k nearest neighbors. Number of dimensions, I've chosen the same number of neighbors and dimensions as before, and we can do all of this stuff. There we go. And hopefully this will just work. So again, k nearest neighbors, it's effectively looking at constructing a nearest neighbor graph, for which here there's no requirement, I guess, that it be connected, because as long as you can calculate the neighbors and do the optimization, you're in business. Oh, it's slow. So that was step 1. There's step 2. I guess no, step 1 was getting the neighbors. Step 2 is calculating ways. Step 3 is computing coordinates. That's rather good luck rather than good planning that those 3 things match the 3 steps. Okay, so here we are. So now we're looking at the Paris plot of the skagnostics. Let me see. Let's make this guy relatively small. our faces, the inspector, and those are the regions that may be of some interest. And you'll see the structure here as before. So looking at those that have high clumpiness. Again, there's an example, as we talked about before in class, of it amounts to 0 sample correlation, but there's an awful lot of structure there. So we force that with Y transpose Y being the identity, but there's still a lot of structure. And we can look at this in a variety of ways. So things that are got lines in them, may as well look for. And we begin to explore the spaces before. 16, 12, 13, 17, 15. So one thing that LLE is being criticized for, quite rightly, is that thing of forcing everything to be centered and have that identity matrix seems to produce a lot of compression into the middle. So you end up having long straggly bits in this dimension reduction. But we could well, let me just get some of these and do the usual thing here of looking at who's here. Set the faces. These guys are. All right, so perhaps not too surprising that it seems to kind of work. I mean, one thing I like about LLE for visualization purposes is that it does tend to produce some lines for clusters, and lines, as we know, are very nice in high dimensional space because whenever you project them, they look like lines in low dimensional space. So I like LLE for reasons that it's justifiably criticized. So all these guys. I think in the interest of time, I won't do the other thing. I have an example here, which I guess I could share with you. We don't have to be stuck with these faces, right? So off on the, if you look at the S&P 500 data where we had 700 and some odd dimensions, do the same sort of thing. Any of these dimension reduction systems, algorithms can work in looking at the scagnostics and structure and having them recalculate the scagnostics based on subsets. You start using all of this interactive stuff, you get to explore a lot more. And as I said in a lecture or two ago, there's no reason not to have several such manifold learning things all at once and exploring, because you can link the plots and see what's going on to some exploration of data. Okay, so there are lots more methods around. You could have a whole course on manifold learning and look at a variety of different methods. It was a very active cottage industry of research for the past decade or more, nearly 2 decades, of inventing different kinds of ways to do dimensionality reduction. And in the DIMREB package, somebody has gathered them together to make them easily accessible for you to play with. And we won't be looking at any more than that. So you've seen PCA, kernel PCA, ISOMAP, and LLE. So yeah, there are others that we could play with. So the independent component analysis and other things. So, ladies and gents, that's it. That's all I'm going to cover this term. There's clearly lots more we could do that would be fun, at least for me, to do. And I think probably you want to have some review of where have we been.